Hey everybody, welcome to our 12th number theory lecture. Today we're going to be talking about Diophantine equations. And what is a Diophantine equation? The Diophantine equation tell you what, let me make that definition right. I left out about 15 words there. I apologize, I got off to a rather rocky start here. I meant what I wrote, but I didn't write what I meant. Okay, let's try it again. A Diophantine equation is an equation in one or more variables that admits only integer solutions. So we can have two or more variables in a Diophantine equation. The catch is that the only solutions that are allowed are integer solutions. I'll give you a heads up right now. We will concentrate almost exclusively on equations of the form ax plus by equals c, where x and y are variables and a, b, and c are known constants. And maybe I should insert something here also. A, B, and C are known integer constants. The only values of x and y that are admitted are integer values of x and y. And the coefficients, the constant coefficients, A, B, C, these are integer valued also. And by the way, can you read that? So the solutions, x and y, are integers, and A, B, and C are known integer constants. Here's how we'll proceed. Our approach will be as follows. First step, determine whether the equation has a solution. That is, determine whether this equation has a solution. And we're told, recall that the Diophantine equation, ax plus by equals c, has a solution exactly when d divides c, where d is the greatest common divisor of a and b. So if we're given this Diophantine equation, ax plus by equals c, and we want to determine if it has a solution or not, find the greatest common divisor, d. And if d divides c, this thing has a solution. If d doesn't divide c, there are no solutions. This has to be the first step. We don't want to break our necks trying to find a solution to an equation that doesn't even have a solution. So the first thing to do is find out, does this equation have a solution? And it will have a solution exactly when, or if and only if, d, the greatest common divisor of a and b, divides c. So if D divides C, proceed full speed ahead. If D does not divide C, give up because there ain't no solution. Now, assuming that D does divide C, we proceed. The second step is to find a particular solution to the equation AX plus BY equals C. This particular solution is just going to be any pair of values for X and Y that make this equation true. So we're just looking for one pair, XY, that will make this equation true. How do we find such an equation? The first step, find a particular solution, X naught, Y naught, to the related Diophantine equation, AX plus BY equals D. And if D is the greatest common divisor of A and B, solutions to this equation do exist. To find the solution to this Diophantine equation, find a particular solution to this equation first, using the Euclidean algorithm. Remember, here's where we were. We wanted to find a particular solution to the related Diophantine equation, and this is not right. There we go. Find a particular solution, X naught, Y naught, to the related Diophantine equation, AX plus BY equals D, using the Euclidean algorithm. So we'll find X and Y values that satisfy this equation using the Euclidean algorithm. And then we'll express the related Diophantine equation in this exact form, plugging in this solution, X naught, Y naught. So we get a particular solution, X naught, Y naught, to the related Diophantine equation where the right side is D, the greatest common divisor of A and B. And we rewrite this equation plugging in the solution that we get, AX naught plus BY naught equals D. Now, what we want is a solution to the equation AX plus BY equals C. What we have is a solution to the equation AX plus BY equals D. So how do we get a solution to AX plus BY equals C from the solution to this equation? Well, if we want the right-hand side to equal C, why not just multiply the whole equation through by C? C over D, actually. Multiply this entire equation through by C over D. So that's our next step. Take this equation, multiply through by C over D, and then take this equation and rewrite it in the exact form of the original Diophantine equation. The original Diophantine equation was AX plus BY equals C. We take this equation and rewrite it in this form. Oh, Oh, and guess what? We have the x value and the y value that satisfy the original Diophantine equation. This is our particular solution. X equals c over d x naught, y equals c over d y naught. Before I erase this, let me just label the x coordinate here as x sub p, and the y coordinate here is y sub p. X sub p, y sub p are the x and y values of our particular solution to the original Diophantine equation that had c on the right side of the equation. Okay, we've got a particular solution to the original equation. Our next step, let's see. Yep, we have a particular solution to the original Diophantine equation, ax plus by equals c. So we have a particular solution to the original equation. The next step, find the solution to the related homogeneous equation. Well, what makes this the homogeneous equation? The fact we have a 0 on the right side. That's the long and short of it. And we know what the solution is. We've already found, in general, what the solution is. The homogeneous solution, which I'll call x sub h, y sub h, is b over dt, that's the x coordinate, and negative a over dt, where t can be any integer. So this is the homogeneous solution. The x coordinate, b over d times t. The y coordinate, negative a over d times t, where t can be any integer. Okay, now we put it all together. The general solution of the original Diophantine equation is the sum of the particular solution and the homogeneous solution. The solution xy of the original Diophantine equation is the sum of the particular solution plus the homogeneous solution. And that homogeneous solution is b over dt, x coordinate, minus a over dt, y coordinate, for any and all integer values of t. And what we can do is add these two things together. The x coordinate of the general solution is xp, the x coordinate of the particular solution, plus b over dt. And the y coordinate is y sub p, the y coordinate of the particular solution, minus a over dt, where t can be any integer. Now, why does this work? Well, I guess we're going to have to look at it from two perspectives. Okay, why does this work? First, let's suppose that our proposed solution, xy, has this form. What happens if we use this x value and this y value and plug it into ax plus by? We take this x value and plug it in for x. we take this y value and plug it in for y, and we'll distribute the a inside this set of parentheses. We'll distribute the b inside this set of parentheses. So we'll get AXP plus A d over dt. Then we'll get B times YP plus B times negative A over dt. And I'll move these terms around a little bit. I'll take this term and move it right next to the first term. Well, remember what it was that x sub p and y sub p were. This pair of values was a solution to the original Diophantine equation. So this is just going to be equal to C. Now, remember what B over D times T and negative A over D times T are. They're the x and y coordinates for the homogeneous solution. In other words, if we plug this in for x and we plug this in for y and add them together, we're going to get a big fat 0. So, when the smoke clears and we add all of this up, we just get C. If xy is our solution, and it has this form, then ax plus by should equal C, and it does. The baggage that we add to the x coordinate of the particular solution and the y coordinate of the particular solution, once we plug these into the equation, they add up to 0. And what we have left is just the right side of the original Diophantine equation. Now, I haven't answered the question completely. What I have done is I've shown that if x and y are equal to these things, and I plug them into the expression ax plus by, I'm going to get C. So what I've shown is that if our solution looks like this, if our proposed solution looks like this, and we plug it in to the expression ax plus by, we do get C. So if our proposed solution looks like this, it is in fact a solution to the equation ax plus by equals C. What I haven't shown is that any solution to the equation ax plus by equals C has to look like this. And I think I will wrestle with that in just a minute. Okay, let's go back the opposite direction. Furthermore, note that every particular solution of the Diophantine equation ax plus by equals C must have the form x sub p, y sub p, plus, what do we call this? The homogeneous solution, d over dt minus a over dt, for some integer t. So every particular solution has to look like this particular solution plus the general, the homogeneous solution for a particular value of t. And here's why that's true. Suppose we have x of p1, y sub p1, and x of p2, y sub p2, both being particular solutions of the original homogeneous equation. What happens if we subtract this guy from this guy? If we subtract this particular solution from that particular solution, we get x of p1 minus x of p2 and y sub p1 minus y sub p2. Yeah, so what? Well, what happens if we take this pair of x and y values and plug it into ax plus by? What happens? If we take this pair of x, y values and plug it into ax plus by, well, let's see, what do we get? We get axp1 minus axp2, yeah, okay, plus byp1 minus byp2. And now I'll take the p1s and p2s and group them together. axp1 plus byp1 minus axp2 minus byp2. Well, what's so special about these things? You see this expression right here? This is what we get when we plug the particular solution, x of p1, y sub p1, into this equation. And we get c. So this thing is going to be equal to c. And you see this thing over here? This is what we get when we take the particular solution x of p2, y sub p2, and plug it into the same Diophantine equation. Since both of these are solutions to the same Diophantine equation, when we plug this pair of values in, we're going to get c. When we plug this pair of values in, we're going to get c again. So this thing equals c, this thing equals c, and we're subtracting one from another, which means that we get a big fat 0. Well, that means something. I think we need to ponder over this for a minute and see exactly what it does mean. Recall what we just did. We took two particular solutions of the Diophantine equation ax plus by equals c. We subtracted one from the other and showed that their difference, when we plug this into the Diophantine equation, or rather when we plugged it into the left side of the Diophantine equation, ax plus by, it turned out to give us 0. So if we take the difference of two particular solutions and plug that into ax plus by, we get a big fat 0. So what does that mean? It means the difference of any two particular solutions, x of p1, y sub p1, and x of p2, y sub p2, of this Diophantine equation is a solution to the related homogeneous equation ax plus by equals 0. You take two particular solutions to this Diophantine equation, you subtract one from the other, and you get a solution to the related homogeneous equation. In other words, the difference of two particular solutions is a homogeneous solution. Let's see what that looks like. We just mentioned that one particular solution minus another particular solution is a homogeneous solution for some particular value of t here. So if we take particular solution minus particular solution, we get one of the homogeneous solutions for some value of t. Well, that tells us something else. Looking at this result down here, I just rearranged the terms. I moved this term to the right-hand side. And what I got was this particular solution, x of p1, y sub p1, is equal to this other particular solution, x of p2, y sub p2, plus a specific homogeneous solution. Particular solution. And you know what? I think I'm going to write that under here too. Particular solution equals some other particular solution plus homogeneous solution. This particular solution is equal to this particular solution plus the homogeneous solution, or one of the homogeneous solutions. Now, let's just turn this instantly into the most general case. What we've just established is that if x of p2, y sub p2 is any particular solution of this Diophantine equation, then every other particular solution, let's say x of p1, y sub p1, has to be of the form x of p1, y sub p1 equals this particular solution plus b over dt comma minus a over dt for some integer z. Every other particular solution has to be of the form this particular solution plus some form of the homogeneous solution for some value of t. So every solution of this Diophantine equation has to look like this. About time for an example. Find all the solutions of the Diophantine equation. 6x plus 9y equals 7. Okay, what's the first thing that we do here? Remember, we don't want to spend all day trying to find a solution to this equation if none exist. So the first thing, just determine whether solutions This is of the form AX plus BY equals C. Now, when is it that solutions to that equation exist? The greatest common divisor of A and B has to divide C, isn't that right? And greatest common divisor is 3. And when is it that we have solutions? D has to divide C, right? Exactly when the greatest common divisor of A and B divides C. D does not divide C. 3 does not divide 7. No solutions exist. Oh, that was easy. I wish they were all this easy. Let's do one where the solutions do exist. Here's a nice one. Find all solutions of the Diophantine equation 534x plus 54y equals 192. And again, the first thing we have to do is find out if solutions exist. I will label this A, B, C. D is the greatest common divisor of A and B. That's the greatest common divisor of 534 and 54. And yikes, I thought this was going to be a little bit easier. Let's see. 534 is equal to 3 times something. Let's see. 1, 7, let's see. 8. Okay. Huh. Does 3 divide that again? My goodness. No, 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 no. Let's see. 4 is not a factor of 178, but 2 is. Whoops, whoops, whoops. 3 times 2 times 89. Let's see. 5 does not divide 89. 3 does not divide 89. 7 does not divide 89. means 89 is prime. Okay. Now let's see, 54 is equal to 6 times 9, and this is 6 times 89. So the greatest common divisor of 534 and 54 is 6. Okay. And I think we have a winner here. Six goes into 19 3 times. And 3 goes into 12 4 times. Yep. So D divides C. We can look for the solutions. They definitely exist. As a matter of fact, we're going to have infinitely many of them. So let's find out what they are. Okay. We want to find a particular solution to the original Diophantine equation, ax plus by equals c. And the first step in doing that is to find a particular solution, x naught, y naught, to the related Diophantine equation, ax plus by equals d, the greatest common divisor of a and b. Well, we found that the greatest common divisor of 534 and 54 was 6. So we want to find a particular solution to this equation. Let's have at it. And do you remember how we do this, the Euclidean algorithm? We take the dividend and we take, well, let's see, we take the larger number and make that the dividend. Take the smaller of a and b and make that the divisor. $534 equals something times 54 plus some remainder, where the remainder is greater than or equal to 0 and strictly less than the divisor. Oh, let's see now. 54 certainly isn't going to go into 534 10 times, but it will go close. So I'm thinking this is 9 times 54. And, oh my goodness, well, let's see, that's 10 times 54 minus 54, okay. Uh, 46, so 534 minus 486. 48, okay, that's our remainder. And what do we do after that? The divisor becomes the new dividend, doesn't it? And the old remainder becomes the new divisor. Oh, and thank goodness, this got really easy really fast. 48 goes into 54 once with a remainder of 6. And then what happens The former divisor becomes the new dividend. And the old remainder becomes the new divisor. Oh, let's see. 48 is a multiple of 6. 8 times 6 plus 0. Okay. I'm going to call this equation 1. And I'll call this equation 2. And what I do is I write greatest common divisor, which is 6, in terms of previous divisors and dividends. From equation 1, 6 equals 54 minus 48. Okay. And I'm going to give this equation a name. I'll call it equation 3. And from equation 2, that's this thing, I'm going to take the smaller of these, the lesser of these, and express it in terms of previous divisors and dividends. So I'll take 48 and express it in terms of 534 and 54. 48 equals 534 minus 9 times 54. Okay. And I'm going to take this and plug it into this equation in place of 48. And that will give me 54 minus 48, which is equal to 534 minus 9 times 54. And I have my greatest common divisor 6 in terms of A and B, 534 and 54. So I just have to simplify this. 6 equals, let's say, negative and negative 9 is positive 9 times 54, plus 1 times 54 is 10 times 54. And I have minus 1 times 534. Okay. And how should I word this? I want to express this in the exact form. 534x plus 54y equals 6. 534x plus 54y equals 6. Okay, I can do that. This is 534 times negative 1. And this is 54 times 10. Equals 6. Well, what I have here are the solutions, or the solution, to the equation 534x plus 54y, x1, I'm sorry, negative 1 is my x sub naught, 10 is my y sub naught. So I'm going to write that down. X sub naught, y sub naught is equal to negative 1, 10. Okay, time to go on to step B. Okay, I've neatened some things up here a bit. Expressed in the exact form 534x plus 54y equals 6. So we get 534 times negative 1 plus 54 times 10 equals 6, which makes this our x sub naught and this our y sub naught. Okay. And then there's step C. Multiply both sides by C over D. The reason we do that, we don't want a solution to the equation 534x plus 54y equals 6. We want a solution to the equation 534 plus 54y equals 192. And in order to make the right side equal to 192, we multiply by C over D, which in this case, let's see, C was 192 and D was 6. So that's what, 32, I hope? Okay. Multiply both sides by 32. So I'm going to have 32 times 534 times negative 1 plus 54 times 10 equals 32 times 6. And I'm going to distribute in the next step. I'm going to distribute the 32 to both of these terms, but watch how I do it. I'm going to take the 32 and distribute it to this factor. And I'm going to take the 32 and distribute it to this factor. Now, why did I do that? Because it preserved the form of the equation that we were trying to solve in the first place. 534x plus 54y equals 192. So this means that 32 or negative 32 is the x value of our particular solution. And 320 is the y value of our particular solution. And 192, well, that's C. Okay. Now let me just check and make sure I haven't done anything stupid. I'm going to multiply all this out and make sure I do get 192. Okay, I multiplied everything out, it works, thank goodness. And what that means is we have our particular solution. It is negative 32, 320. So I guess now the thing to do, since we have our particular solution, is to find that homogeneous solution. Okay, we're getting close. Find the solution of the related homogeneous equation. That's just the original equation with the right-hand side set to 0. The coefficient of x is a, coefficient of y is b. And our homogeneous solution is equal to b over d times t, negative a over d times t. So in that case, that's going to be, let's see, b is 54 over 6 times t, negative 534 over 6t, and what does that turn out to be? 9t minus, what, 89t for any and all integers t. Okay? So here's our homogeneous solution. Nine t minus 89t for any and all integers t. Holy moly. We're things close. I can just sense it. The general solution is the sum of the particular solution and the homogeneous solution. Here's the particular solution. Here's the homogeneous solution. And we can leave it like this, or we can combine into one ordered pair. This is our x, and this is our y. And let's see what the ramifications of this are, for lack of a better word. This is our solution right here. Let's just play with this for a second so that we know exactly what it means. We can let t equal 0 and xy becomes negative 32, 320. Well, we don't have to plug in t equals 0. Maybe we'll plug in t equal 1. Excuse me. I still haven't discerned the difference between 1 and 11. Maybe I'll get there before my 80th birthday. If t is 1, then xy becomes 1, negative 32 plus 9t. So that would take us to what? Negative 23. And let's see, 320 minus 89 is 231, I think. So here's another solution. What about t equal 2? In that case, we get the solution negative 32 plus 18 is negative 14. And 320 minus 89 times 2, let's see, what is that? 178. 320 minus 178. Holy moly, what is that? Let's see. Let's see, is that right? Yep, okay. Now, we can continue on. T doesn't have to be a positive integer. T could be a negative integer. And that would give us yet another solution. Let's see. If t is negative 1, we have a negative 9 here, so that'll give us negative 41. And that'll give us positive 89 here. So that's essentially how this formulation of our solution generates all solutions, and there are infinitely many. Well, I'll tell you what. I've talked about almost all that I need to talk about when it comes to Diophantine equations. There's one thing that I really haven't talked about yet, and I'm not going to talk about it now, but I'll talk about it in part 2 of this lecture. And what that has to do with is applied problems of this kind, where maybe it doesn't make any sense to have a negative number of something. For example, how many quarters, nickels, and dimes do we need to put together to get $48.35? If we let x be quarters and y equal dimes and z equals nickels, they can't be negative. We can't have a negative nickel or a negative dime or a negative quarter. And so we'd have to craft our solution or restrict our solution set to those cases where x, y, and z, the number of quarters, dimes, and nickels, was all non-negative. So we'll look at examples of those types in the next lecture, which will be forthcoming in about a day. A lot of this lecture was theory. The next lecture is strictly going to be problem solving.